So next up, we got Dave White. He'll be, and that's again the binders on desk. I guess Dave is going to refer to those binders. Dave, we've had a long partnership with Dave White, both when he was at Iowa State. Now he's moved on, has his own company in Geos. He's helped us out a great deal at Minroad, just a couple times, but particularly in the last year with the reconstruction. Was out there again yesterday. Hopefully you got a chance to see his equipment. And there is just a reminder that on the Geotech page for NARA, the report that Dave produced for last season's construction, all the mapping that was done on all those sections out there, that report is posted on the website. And if you happen not to locate it, just shoot me an email and we'll get that to you. So thanks a lot, Dave, for being here again today.
You bet. Thank you. Good afternoon again. I'm going to go through a slide deck and refer to the binder a few times. I put together this binder so you'd have something to take with you on this topic of pavement foundation QC/QA. The emphasis here is mechanistic, and I think it's a really big deal for the geotechnical community and the pavement engineering community to transition to mechanistic QC/QA, and also process control. I think that's going to be a really important element as well. So I'm going to talk about some approaches that we're using, and again, the binder has some documents I think you might find helpful as we go through. So let's see. Or do I just hit the advance on this? That's not working.
Do I clicking on the slide?
Touch. Okay. So why are we talking about mechanistic QC/QA? And you'll notice I added PC. I think we really need to be talking about process control. That's kind of inherent in QC, but with intelligent construction technologies, we have the ability to allow contractors to control things in real time. That's a little bit different than QC testing. So we have a history. Our design methods are improving. We've introduced mechanistic parameter values that are stress dependent. So that's pretty great. There are a lot of things happening nationally, especially with design standards. They're becoming easier to use. They're being implemented. They support performance-based material selection. Geotechs were kind of lagging behind a little bit. We've got a lot of catch-up to do to match these efforts. So just a little background information. When we talk about resilient modulus, this is a parameter value that's stress dependent. So we really can't talk about a resilient modulus value. It has to be tied to some condition of stress. So an example of that, this is what we call our Faribault Clay. This was collected south of here, and we've been using it in a lot of our studies. So for different levels of confining stress, we get different responses of modulus. And this is a class 5 aggregate base. This was collected from a St. Paul quarry that supplies material for MnDOT. Again, the response is stress dependent. So a big difference between subgrade clay material is that they tend to soften. Modulus goes down with increasing stress, and it's the opposite for granular material. And if you look at the scale here, 0 to 60,000 PSI versus 0 to 7,000 PSI. So pretty big difference. And we have this short form of the universal model that allows us to relate resilient modulus to these coefficients. It's really just a curve fitting exercise, but K1, K2, and K3 help define a model that captures this stress-dependent behavior. Moisture is also a really important aspect, and I think Dr. Nazarian is going to talk more about this. There's an approach that's published in the MEP design guide about how to correct for moisture content. So that's what's shown for subgrade is the dark line, and the blue is for coarse grained. And then this data over here is a real sample. That happens to be one that we've tested in comparison to MEPDG, and it's pretty good unless you deviate moisture content very much from optimum. Then it kind of falls apart a little bit. So we have an approach. Now what we've been doing in the field is we've been measuring the in situ composite resilient modulus and calculating layer resilient modulus values for stresses. And one of the complicating things in the field when you test aggregate materials over subgrade is you get these really interesting stress dependent curves. So this one shows as stress is increasing, modulus increases at a certain point. We call that the breakpoint stress. And then with increasing stress, modulus goes down. So we have a composite system, aggregate over subgrade. As we push harder and harder, the effect of the softer subgrade beneath is dominating that composite modulus. And then we look at permanent deformation as well. And from these responses, we can develop a model that describes the stress-dependent stiffness. And we do this from applying cyclic loads and monitoring how much rebound we get. Interesting, the gentleman from Illinois that showed the picture from the Illinois ASHO road test. When you go back and look at the geotechnical data, they used cyclic plate load test results to calculate modulus. They only did 6 cycles though, and it had to be done, it was probably a lot of work back in the 50s when that was done. So we're really not inventing this thing, we're just going back and getting the data. But now we can do hundreds and thousands of cycles to capture that response. Static testing is also applicable. So this is pressing, maintaining the load, monitoring the response, and this would be an example data set. And you can load it, unload it, and reload it. When we look at some of the tests that we've done, we can compare them to typical values in MEPDG. And it's interesting that the in situ results compare fairly well with K1, 2, and 3 with laboratory measurements. And we've actually, right now we've got a federal STIC project with the Iowa DOT to develop this database statewide to help them with a statewide calibration. We really like plate load testing. We've done a lot of other testing. We've done laboratory testing. We've done FWD testing, LWD, DCP, CLEG, and all the other devices. One of the reasons that we really like plate load testing is boundary conditions. In the field, we don't have to concern ourselves too much with boundary conditions. We measure what's there. If we do it at enough locations, we can get a pretty good idea on what's happening. When we bring materials back to the lab, things get a little bit more challenging. Lab testing is great. There's some things that we can do in the lab that we can't in the field. But as an example, for this class 5 aggregate that we got from the quarry, in the laboratory we'd get resilient modulus values on the order of 50,000 psi. In the field, we get values that are 15 to 25,000. And a big part of that is because of the boundary conditions in the field. The softness of the subgrade are dominating the behavior. One project, I touched on this earlier, we had an opportunity to do about 100 tests on an existing pavement down a core hole. These are just a few of the pictures. And on interstate, sometimes you got to work at night because the traffic's ridiculous during the day, so they don't let us out there. So this was an interesting project. When we look at the modulus for material that was put down in the 50s, it's a little bit softer than the material put down in the 70s. It shows this stress softening behavior. Look at material that was put down in the 90s, it's pretty great. This is more of a granular type response. The higher the stress, the greater the stiffness. So those are some of the things that we've been looking at from a mechanistic perspective. So that's a little bit of background. Now, when it comes to implementation for mechanistic QC, QA, and PC process control, these are a few of the things that have to be considered. Stress dependency, moisture dependency, and I would encourage, if you're thinking about doing this, you really need to develop a workflow process. To do this correctly, the design people have to be talking to the geotechnical people, they have to be talking to the field people, and somehow this has to be translated to a contractor so they can build things to meet the design requirement. And this is our approach at this point for doing that. So there's multiple steps on the design phase. You have to select inputs, layer thickness, material, design loads, layer modulus coefficients. You've got to calculate stress on each of those layers. And then you've got to translate that into some target value that can be measured in the field. So in the field, what we're doing a lot of right now is plate load testing, either in static mode or cyclic mode, to match those up with the design values. And there's a lot of detail in this, but the workflow process to make this happen within an organization can be a bit complicated. And just getting people to talk and kind of speak the same language between design and construction can be difficult sometimes. So I would encourage you to think about creating this workflow process. That's, I think, a good starting point for implementation. So now in the binder, why I put this together, you can refer to tab 1 if you want. You can flip that open. And I've created an example problem. This is your homework assignment. The great thing about this exam, though, is that if you turn the page, the answer's provided. So you don't have to get your calculator out. So one of the things that we have to do when it comes to field verifying Modulus is we've got to understand the design, figure out what the loading conditions were, what kind of stress level are we anticipating in the different layers at the interface, and then run tests appropriately to capture that level of stress. So for this example, the vertical stress at the interface is calculated as 30 psi. And there's a nomograph. This is from a well-known textbook that allows you to do this pretty quickly, figure out what that stress level is without having to go through all the calculations by hand. So then what we need to do is, when it comes to in situ testing, we want to figure out, okay, at the base interface, we've got 12.2 psi, at the base subgrade interface, 5.9 psi. For these different anticipated modulus values. This would be for a 3-layer system, which is what we were testing in Minroad yesterday. So we can do that. And then what we can do is we can run a test, make sure we capture the range of stress. We can back calculate using an APLT back the modulus values for each of those layers. And then given that design stress in our universal model, we can calculate then the modulus for both the base and the subgrade. So it's a pretty straightforward process. We haven't invented anything new here, but I think it's helpful, especially for the Geotech folks, to be able to take a design value and translate that back into a field target value. And then we can make a correction for moisture content. So there's basically 2 approaches we're using right now. One is per the MEPDG moisture correction factor. And then the other is by actually taking samples and running a test. We can't be afraid to run tests on these materials. They're really complicated materials. I love all the empirical stuff, but when it comes down to it, I prefer testing. This one's kind of interesting because if you look at the correction for the subgrade, it was about 14,000 psi before the correction, and after the correction, about 7,000 psi. So it does make a difference. So that's a little bit of the technical details. Also in the binder, we've included an updated test standard. So I mentioned the old AASHTO road test in Illinois. There's been a test standard both in AASHTO and ASTM for a number of years that describes repetitive plate load testing. And it's pretty simple. There isn't a lot of detail in those test standards. So we've taken on the idea that we really need to refresh that. So we've rewritten the test standard, and you've got a draft there. At some point, we need to move this thing forward and get folks who are interested in looking at this thing together and review it and go through the formal process. Okay, so this is an example project. This happened to be on an Illinois DOT project. So they're placing subgrade, and it's fat clay subgrade, variable moisture content. A lot of variability, coefficient of variability upwards of 100%. And if you look closely here, you can see that this, I think this was an 815, isn't walking out of the clay. That's usually how you get a visual on whether or not this material has been compacted into a stable condition. The machine will walk out. And it wasn't doing that, it was just wet. And the contractor came up with a fantastic idea to improve compaction, which was instead of just rolling it the longitudinal direction, to roll it in the transverse direction. And that had no effect on improving compaction, okay? But it was something that the contractor was trying to do to make things better. What they needed to do is just reduce the moisture content. It was as simple as that. Aggregate materials vary in gradation. They become segregated. The stiffness varies. We saw a lot of variability with that as well. And so we came up with a test program that varied the size of the plate. We had a lime stabilized layer, this fat clay subgrade. We had a CA6 virgin crushed limestone material. We had different stress levels, measured deflection basins, so we could calculate all the necessary parameters. And on this project, what we found out is that there's just an awful lot of variability in these mechanistic values. And these were actually research sections. They were built to support research pavement sections. We're working on a paper with the University of Illinois and ARA, one of the tollway consultants that was involved with the research to publish this. But it's really interesting to me to see how much variability there is in the foundation at this site and in many other sites. And I've talked about this before, but one of the challenges that we have is really from a design standpoint, we don't have an approach to deal with variability. Actually, we just sort of ignore it because we can't deal with it. So I don't know that that's a good approach to have. I think probably a better approach is to somehow deal with variability, to measure the correct things, change the field process control so that we can account for it. And I've shown this slide before, but I think it's worth mentioning again. So in a lot of these projects, when we measure mechanistic parameters, we see a lot of variability. That would be the blue line. And we're seeing this in Iowa right now with our statewide calibration. Essentially, there's one number used, 150 PCI for modulus subgrade reaction for the state. But there's all these different materials and conditions that exist. So on our projects, we're seeing this variability. So the question is, what do we do now from a design standpoint that we know we have these variable conditions? Do we adjust the design value? I don't think so. I think what we do is we figure out how to build things so that they're more uniform, so they meet the design requirement. Does that make sense? Would you change the design requirement? Or would you try to build things to meet the design requirement. Or who cares, right?
We need to do something.
We need to do something. Yeah, I agree. We've got to do something to make this work better. Another thing I want to mention is that for whatever reason, from geotechnical engineering, with the very materials that we have, the challenging conditions, our sampling is just absolutely terrible. I mean, we have so little data when it comes to these projects. I don't know if anybody agrees with that or disagrees. I kind of beat my head against the wall when I look at this statistically because, you know, I was out at Monroe yesterday, kind of checking things out. And what I saw was, I saw damage in some sections, which is great because you learn from it, but it wasn't damage for the whole section. It was damage that was isolated to areas. And you see that a lot on pavements. The whole pavement section is not falling apart. It's isolated locations that are having problems. And a lot of that has to do with variability and not sampling the locations that are going to have problems. So when we look at it statistically, you know, there's like a 90% risk when we build roads using conventional testing that they're built-in defects that we don't know where they're at, but they eventually will show themselves in the form of pavement distress. The only way to fix that is to do a lot of sampling, and we can't do that because we don't have the money, the people, so we've got to change test methods, we have to use technology. So we're really excited about the potential for intelligent compaction to serve as a really important inspection tool in this process, because it gives us a lot of information, allows us to identify these areas. When we do that, our risk goes down substantially. When we have the information, we can find these spots. So we've now, and this is also in your binder, been working in Illinois to draft a new specification. There's a little bit more teeth to this specification than you've probably seen in prior IC specifications. And when I say teeth, the data has to mean something. It can't just be an index value. It has to relate somehow to some mechanistic parameter that's important to the project. And we've got to be able to relate that to a target value on the project. And that's a big change, I think, in the direction we're headed with these specs. And we've done enough projects now. We've figured out how to make this work, how to get mechanistic parameters for range of materials, and do it in a good way. So I showed this earlier. This is one of my favorite plots because during the mapping, and I happen to be operating the roller, it's like this is not good. This is not going to work. And we were doing it at the end of the day. And the next day, that morning, the QA team came in and did their routine inspection and passed everything. And I'm like, no way. This pavement just got built on something that has a severe defect built into it. And in my mind, I'm like, I know where the cracking is going to occur. And that pavement's out there, and I'm going to keep my eye on it. But you know, the sampling wasn't adequate, and you know, talking to a lot of field personnel, it's really interesting because when you talk about Modulus, a lot of field personnel are, what are you talking about, dude? You know, I'm doing some density testing, I might be doing some proof rolling, but talk about stress-dependent modulus, you know, that wasn't part of our training. So if this stuff is going to be implemented, there's going to have to be some proper training to help the field people understand why this is an issue, what modulus means, what target values are, how we go about testing to establish these things. And that just, again, is some of the evidence from that section. Now at Minroad, we participated and were able to go out and test some of these different profiles, and I'm just going to kind of flip through these. You know, there were some soft sections, there were some really stiff sections, very different results comparing the sand subgrade with the clay subgrade. The stiffness of the aggregate base is much higher with good support in the subgrade. So just kind of flipping through those again. You know, we see non-uniformity. We see that pretty much on any pavement foundation mapping that we do. And now we're working on some new tools on how you deal with non-uniformity, how you identify those spots and fix them. So that's also in the binder, there's some discussion there to outline how do you go about calibration testing. So if you want your IC data to be meaningful, you want to calibrate it, how do you go about setting up a test program to do that? It turns out that it's dependent upon the field conditions, the material types, how much variability is there. So in this one example, to calibrate, you've got to do about 6 tests. If you do that with a system, this was our VIC system, you got to do 6 tests, you get a reliability of 88%. And then if you do that with a system that is putting out more variable data, the number of test measurements just blows up. So what this is telling us is that if IC data is going to be used for QC, QA, process control, the output from the data has to be meaningful. It can't just be an index. It's got to be related to something like a mechanistic parameter value. This is another element. We're not sure what we're calling this yet, but we'll call it the Intelligent Inspector Initiative. And that's probably not going to be the right terminology because I think inspectors are already intelligent. But we're going to add a feature that helps them be a little bit more efficient with testing. So this is a set of IC data that was generated, and we've added an algorithm that processes that data and eliminates a lot of traditional QC QA testing. I talked about the fact that we don't do enough testing, and now I'm telling you we're going to reduce it even more. Okay. The only reason we can reduce it more is if we have a proper calibrated map. And the beauty of this is that it's fairly inexpensive to generate this IC map relative to conducting spot tests. What this algorithm does is it zeroes in and prioritizes areas for testing. So if our priority is to find areas that potentially could be problematic in the future, it's going to zero in on that hot spot. And we're going to go there and we're going to test it. And the reason that we're going to test it is because we want to know why that hotspot showed up. We're not necessarily going there to test it to approve it, but we want to know, is it a wet condition? Is it a deeper issue? Is it a change in material? Was it just poor compaction? So that's kind of the mindset that we've taken with that initiative. So something we're working on. And just to kind of give you a feel, that's a modulus of, 3,000 on the left on subgrade. And that's a modulus of 25,000. You can hardly see it move. I just like showing this and watching that thing sink in the ground. I think it's cool. Now, when that sinks in the ground, the permanent deformation tends to follow this red curve. We reach a bearing capacity failure. That's not a good situation. The green's kind of intermediate, and the purple's kind of where we want to be. We want to be able to push on things and not accumulate permanent deformation. Yesterday, I tested 4 sections out at Min Road, and we generated permanent deformation on the asphalt layer between about 0.04 inches and 0.11 inches. So the one that was 0.11 inches left a small indent in the asphalt surface, but it was because of the underlying foundation. We're kind of in this intermediate situation there. Now, just to kind of wrap up, we've been doing this mechanistic testing. We've been measuring resilient modulus. The thing that is standing out for me is that we have a serious problem with permanent deformation of our foundation systems that's not being addressed with inspection, and it's not being addressed with design. The reason I think it's a serious problem is because when we take the measurements and we model the pavement structure over those conditions, we can see that what we're observing with cracking and failing is matching up. And this was kind of an aha moment for us because we were on a project and we were measuring modulus, and we measured modulus here and we measured modulus here, and it was pretty similar. But the permanent deformation over there was much more than it was here. So from a design standpoint, we're treating it all the same. Probably shouldn't be though. So this is something that we've really just started to focus in on and look at, and I just wanted to throw you out there. We've talked a lot about modulus, but when it comes to mechanistic parameters, let's not forget about the permanent deformation component. I think it's really, really important. And with that, do we have time for any questions?
Must be no questions out there. Dave has challenged us with a lot of stuff, I think, so. There you go.
So the idea with that automated detection is you're looking for kind of the worst case scenario spot, the spot that you'd anticipate would fail first, and then saying, okay, this core is more valuable, or this sample is more valuable than it would have been had you just randomly selected it. That's kind of where you're going with that.
Yeah, exactly.
And then how do you have any plans for differentiating if that sample is in fact caused by a material change, or, you know, what's the thought process on how to handle those situations?
Yeah, so it's a great question. And
Maybe repeat, maybe paraphrase what he.
yeah, so with the map that showed the hot spot and zeroing in and performing a test there, an independent test, our thinking is that if we're gonna have people out there doing this testing, let's do it in areas that are gonna provide the most value. And those hot spots are really valuable because we can figure out what didn't go right. And if we can figure that out, we can change our process. And then the contractor can recognize, okay, I've got a hot spot and it's a moisture issue, or it's a different material, or an underlying issue, or something else. Those issues are kind of field or site specific on exactly what they are, but we'll work with the contractor to develop a work plan early in the process. So if things aren't going right and we're seeing these hot spots, what's the action that we need to take? So it's a little bit different reason to do the spot testing. We're pushing to use the mapping results more for acceptance and identifying those locations. You can still do acceptance independent testing, but we want to use that measurement to really help the contractor understand what the process improvement should be.
So if I'm understanding correct, that hotspot is more get it out early enough that it's a quality control type feedback versus acceptance, because then you run into problems. Are you judging equally between projects? Because like you said, if you have more variability in your material, then it could be more difficult of an acceptance, I guess.
Right.
Okay.
Yeah. You got it.
Other questions? Okay, thanks a lot, Dave.
Yep.
We sure appreciate Dave's partnership and